Good morning, everyone. Good morning, all participants. Before we begin, I would like to share a few important announcements for all the participants. Please ensure your microphones remain unmuted during this session. You may post your questions in the chat box, which will be taken up during the Q&A segment. Kindly join using the same email ID or same name which you have used while register, so your attendance can be recorded properly. So and submitting your daily feedback and assignment is mandatory for receiving the participation certificate. So we start the session. Good morning, everyone. A warm welcome to all the participants to the ninth session of our AICT Atal Faculty Development Program on English 4.0 organized by Mahavir Polytechnic. Today's session will be delivered by Dr. Kumari Ambe Verma on the topic Computational Fluid Dynamics for Advanced Thermal and Fluid Systems in the Industry 4.0 era. Dr. Kumari Ambe Verma is currently serving at IIT Bhopal University, Madhya Pradesh, and has also worked with the Madanpalli Institute of Technology and Science, Andhra Pradesh. She has earned her PhD in Mechanical Engineering from the National Institute of Technology Future with her research focus on supersonic combustion, CFD and propulsion system. She has also served as senior researcher at Gyeongsang National University, South Korea, and has over 23 publications in reputed science and Scopus Index journals, along with several book chapters and conference papers. Her expertise covers CFD, combustion, supersonic flow, and advanced simulation tools like ANSYS Fluent, COMSOL, MATLAB, and CATIA. We are honored to have her with us today to share her valuable insights on the use of computational fluid dynamics in modern thermal and fluid systems aligned with the Industry 4.0 framework. So, welcome, ma'am. We look forward to your enlightening session. Now, the virtual platform is all yours.
Thank you so much, sir, for the warm introduction. I like a lot. So let me share my screen. I think it's visible to everyone.
Yes, ma'am, visual. Please make.
Am I audible?
Yes, ma'am, you are
Yes.
audible. Your screen also visible.
Screens are visible. Okay, thank you so much, sir. Thank you, AICTA. Good morning, everyone. My name is Kumari Ambe. I thank AICT Training and Learning FDP program organized by especially Mahavir Polytechnic, Nashik. And special thanks to coordinator and co-coordinator for inviting me to give a talk on this session. So this is day 5 of the session, 9 topic. So today talk would be all about CFT related to advanced thermal fluid system that we can align with the Industry 4.0 era. So these are the session contents, starting with the introduction and little bit motivation, why you should focus on CFD and how it is interlinked with the Industry 4.0, fundamentals and the understanding of thermal fluid system, how CFD can connect with the advanced analysis, how we meet with the Industry 4.0, certain opportunity in research and education. Why? Because people are here mostly from the researcher education and somewhat industry delegates also, and few students can get benefited from this discussion. So we'll start with the introduction. In the modern engineering system, people are more involved with the complex problem such as flow, heat, energy, and which material we should choose. And these things we cannot perform the multiple analysis with the experimental. We have to need certain virtual tool where we can get the optimized solution, not the single solution. We cannot perform multiple experiment and get the one. It will be not cost effective also. So for to remove this thing, CFD enables virtual experimentation. So what we are doing here, we are talking about the CFD that play a key role, will combine with the Industry 4.0 technology that will enhance the optimization, safety, energy efficiency. So in overall things, one can say if you cannot measure it, simulate it. So one topic among many engineering problem is thermal fluid system that manages heat and fluid flow. So you can see three pictures I quoted here. The first is all sources from internet. You can see the laptop right now you are using always have a one very big problem is heating. Now second you can see the EV vehicle here also Here also you can see you can consume the energy, but the heat dissipation may reduce the performance. And the third image is all about the thermal management device. Wherever heat dissipation is occur, we used to settle certain kind of apparatus. For the laptop also, you often utilize the external fans and many things. So to overcome all the problem, there is a tool we call it as a CFD. Many other tools are available, but CFD can be a hero for this modern engineering. So if you will go to the history, traditional design, earlier what we do make a prototype, then analyze it and then simulate it and get the result. It was costly and slower process. Modern engineering focuses on visualization tool. Make a visualization tool with the help of certain softwares, fast and optimized way. Nowadays, people are connected with the intelligent tools. Nothing but AI tool, digital twins are available. So we are now in a very fast and forward mode combining with the COD. So let's take one picture that represent all the things that has been happened since 1780 to now, and now people are more searching or going ahead into industry 5.0 also. So let's see the first 1.0. The starting with the mechanization, then mass production, automation, electronics, information, and now we are here in the industry 4.0 talks about all the IoT, cyber physical system, cloud computing, robotics, industrialization, and how we can achieve all those things because we have to enhance our capacity in multiple tools. And the next coming industry 5.0 will be all about the resilience and the sustainability. Still, we did not reach. That's why we are talking about the industry 4.0. So it's all about the introduction and motivation. Let's go for the little fundamental. It's not that complex. If you know little mathematics, physics will be more than enough. So it is computational fluid dynamics. It's a branch of fluid dynamics where we will use computer to simulate the all the governing equation that utilizes the basic fundamental.
सबमिट
So
करा
as you
परफॉर्मेंस
know,
हो
there are
जाते
three basic fundamental. We'll discuss later. Before that, if you are aware of certain any tool that utilizes the computational tool, where it will categorizes into three that you can see here: pre-processing, solving, post-processing. All have different meaning. In pre-processing, we always set the problem. In the solving, the computer will play the role, and the post-processing, the interpreter will visualize the thing. So in CFD is nothing but the watching a fluid motion in a computer. So this is a one pictorial view you can understand. In the first segment, we will design it, will make a certain changes in the geometry. We call it as a meshing, and then we'll give the initial boundary conditions and many conditions. And the solving part, the second in the middle, you can see it's all about the computer part, where you will say to the computer, use this equation, solve my PDEs, and then the computer will solve and will give you the visualization and in the result part. And you can post processes with the help of multiple visualization too. So if you can see one very easy example I have taken, it is a one-fourth part of the one circular disc. So you can see in the first, it talk about the build geometry. So what we will do, we'll make a one geometry form. Then in the second part, we will do the messing part. People are aware of what is messing, but we'll discuss these things. It call it as a grid generation. Sometimes we call it as a discretization tool. Names are different because of the meaning. So here you will do the small segment distribution. You'll do the third. You will define the boundary condition and the set of domain condition. Now once you are done, we call it as a pre-processing. You will pass the same information to the computer, and where you will say utilize this certain equation based on your demand, whether the domain is related to turbulence, whether it is related to combustion, whether it is multi-phase flow or fluid structure interaction. That all the condition you will say to the computer, and it will start doing the calculation, converting PD to the algebraic. And then the visualization tool will call it as a analyzing and interpretation. So you can utilize multiple post-processing tools. So this is a basic understanding of any CFD. Now talking about the aerospace or talking about the application, people might be more curious where we can utilize CFD. There are multiple dimensions you can connect anyway. So if I'll talk about the aerospace, starting with the aerospace segment, you can see I quoted one is TRDO HSTDV. This is the scramjet combustor. My domain is related to that. That's why I quoted here. So they are simulating it because we cannot make the high speed combustion analysis in the wind tunnel, and it is really costlier and difficult to analyze it. So we do the CFD analysis. Now the other things, rocket, what are the pressure distribution is going on at a hypersonic launch vehicle, what are the wing body interaction, we call it as the fluid structure interaction, how it will behave in the combination of solid and the fluid behavior, because at a higher speed you cannot understand what is going on. It will not be the normal at the land, and many more. So talking about the real time application, you always go for the refrigerator. So there is a pipeline backside, you always see how they have decided that it will be kept upside downside, what are the domain. You can simulate it and analyze where the heat flow resistance are more or less, and you can keep it accordingly. Now this is more popular thing, automobile, people know. So automobile is a combination of internal external analysis. If you are talking about the aerodynamics, the designing part, it's a different section. If you are looking for the engine cooling, it is a different analysis. Similarly, interior ventilation also one task, so that the driver or the people will be feel comfortable while driving. So this also you can analyze here. Now talking about the biomedical, people don't know the mechanical, always mechanical engineering people and these people always invest in the biomedical. They focuses on the heat dissipation, cancer growth, everything we can analyze with this software. And you can see the one example, that is temperature natural convection. This is the eye cataract, where the laser heating can change the behavior, can disrupt our eyes. That also we can analyze in this CFD tools. And chemical processing, like how to mixing will happen, what are the twin screw extruder we should utilize, what are the modes of the flow we should take. These are all about chemical processing. Go for the HVAC, you are more aware nowadays. People are more looking for the air condition, how you will keep it, what would be the size of the volume, how the duct will be designed so that the efficiency will be higher, there would be lesser loss, because we engineer always focus on reducing the error, whatever the inefficient part, try to get the 100% efficiency. And hydraulic, it is really good example, because you can see there is a bridge where both side fluids are available, but there is one catch here. You can see the air also play the role to designing this part. You cannot ignore the air, wind speed, and any disaster situation. So it's not the only the one bridge is standing in the middle of the water, or the whatever the dam, it's middle of the water, water streams. It's really difficult to simulate. For that also multiple category we have defined. Now marine is really big now. Ship hulk is, people are working on this, the front head, how to design so that the
Agree
drag
to
will
with
be
the
normal and
electrical
the
also
speed
that
will be higher of the machine. Similarly for oil gas, you can see how you can make it possible, the whatever the pipeline you are talking about, how the flow vectors and pressure distribution on the offshore oil rig. This category always go for the mining people. They make a drill in such a way the
हाँ
life of the drill bit will be higher and will be efficient also. And now talking about the power generation,
मी काल त्यांच्याकडे दुसरा फोटो मागितला होता म्हणलं
burners,
थोडासा फोटो असा त्यांचा
industrial
क्रॉस
burner
होतो ना
is really popular
थोडा
in
प्रोफेशनल
combustion
फोटो द्या
domain. What are the
त्यांनी तोच
flow
फोटो पाठवला
pattern in the
आणि
water
सांगितलं ये
turbine and the
मला
cooling
खाऊ जाऊ
towers,
दे पुढे
everything.
फोटो
People
चालू
are
होतो
working in this
लेक्चर देते ना बस
mostly flow around the cooling towers. It is really important where you should keep all the towers so that the other will not radiate or transfer the heat to the other domain, because one will can affect the others also. And the last and really important, recently you can see the World Cup. Now here swimming is also one of the really major part, where they have analyzed how to keep your hand so that the disturbance inside the water stream will not give you resistance. It will allow you to go forward. So these are the really good example among the application of CFD. You can choose accordingly any domain you can solve, but you have to be very caution how to choose the solver, how to make grid generation. These things we'll discuss soon. So you can see here the understanding of the thermal fluid system. Now we are planning to talk. Now introduction and fundamental of CFD is all about how the application will work, what are the domains, what are the three major section: pre-processing, solving, post-processing. Now let's go for the little mathematics and physics. So as you know, any basic thermal fluid system definitely will take three major direction. So first would definitely be the mass, second would be momentum, and third is energy. All are aware of this. So we always talk about mass is conserved, momentum is conserved, and the energy is conserved. So in the momentum, we know the Newton's second law is the major thing, where the force will distribute it. Like force is whether the pressure force, the weight force, what type of force we are talking about. So all the fundamental physical equation will try to understand, and then we will choose our problem, what is the what are the additional equation we can add, and then we'll give it to system. The system will simulate my problem. Now, being a mechanical engineer or engineer, you must aware these two words, Eulerian and Lagrangian approach. This is all about how would you analyze the product, whether you are standing and the flow is passing, or the second condition you are passing with the flow stream. So this is two major approach, Eulerian and Lagrangian, where we can say the particle is standing or traveling with the fluid motion. In the CFD, we call it as a conservation form and non-conservation form. We never say Eulerian and Lagrangian. So we say the control volume term, we say the control surface term, where the picture you can directly understand in the control volume, it is fixed and the streams are flowing. We call it as a conservational. And here you can see the particle is moving through the streamline, whatever the streamline. It can be heat flow, it can be fluid flow, anything you can say. So this is all about conservational and non-conservational. Here we never say Eulerian approach and Lagrangian. People talk about the fluid particle trace and the control volume trace. So here we'll say the flow model which is fixed in space, conservational form. Flow model is moving in the space, we say non-conservational form. This is a one keyword you must know while doing the analysis. And now people will say how we can connect both. So there are material derivative already available in the mathematics that connect the Lagrangian and Eulerian together. In Lagrangian, we utilize the substantial derivative, and in Eulerian, the temporal changes, convection changes terms are involved. And you can understand the picture. All the this picture I have taken from internet. It was easy to understand. Let's go for few equation. You might be aware of this equation. The might be more aware of this conservational form. The density is dependent on time, and this is the space derivative xyz. Once you will open it, you will see it talked about the densities changing with time and the space. If you will convert into the non-conservational form where the particles are moving also, this material derivative will play the role. Similarly, for the, okay, I gave left and right where you can see I wrote for the viscous flow and for inviscid flow. Inviscid flow where the viscosity is constant. In continuity, there would be no change in the equation. Once you will jump to the momentum, that we call it as a Navier stroke equation, you can see I shown a lot of equation. Just be patient. You can see here the rho u is nothing but the momentum. It is dependent on time, and now it is dependent on space also. And this del p by del x, you can see this is a pressure term. And now tau is all about the viscosity term in all the if it is a control volume, all the phases with respect to space. Now go for this rho effect. This is a weight, nothing but the body weight we are talking about. So if you will combine in works direction, we call it as the x momentum component. Similarly, y momentum, similarly z. And now what is the catch here? If you will eliminate this tau term, it will be inviscid flow. And that inviscid flow equation, we always say the Euler equation, because inviscid flow never take place in the Euler equation. And whenever the pressure term with the shear stress and this term, you will see all about Navier-Stokes equation. Similarly, you can see the non-conservational form top side. These three equation utilizes the material derivative in combination of both. So there is no different in the mathematics. It's about how would you represent it, whether you are tracking the particle with the flow or whether you are a fixed and watching the thing. It's all about you are in the boat, and boat is flowing in the water stream, and the second is you are standing at the bridge and you are looking the particles. So it is like in this way. Similarly, for energy equation also, the inviscid and viscid flow, viscous flow, where you have seen one term that you can see E and V square by 2. It energy can be any form. Here the fluid thermal fluid system, we focuses on the internal energy and kinetic energy. So these terms we have segregated. All the internal generation, all the effects that happen, we it is in the right side. So this is a conservation, non-conservation and conservation. Only one catch you can see here, it is a viscous and inviscid. Definitely you will not see any tau term, see stress term in the equation. This is the basic equation you must understand before heading for the CFD. So if someone will tell you the governing equation, we call it as a fundamental principle. Mass is conserved, Newton's second law, momentum is conserved, and the energy is conserved, where all the terms are important. To use this equation, you cannot give to this computer immediately. You have to give in a discretized form. Why you have to give things in a discretized form? Take an example of one room, and you wanted to calculate the temperature at the middle. How would you calculate if you're giving only two boundaries? So we create a multiple imaginary boundaries and we small segment part. We call it a discretized form so that we can understand the each and every location. The equation will be calculated, will not jump, and then you can calculate each and every places. So here in CFD, it is the art of replacing the PD equation into equation of the discretized algebraic form. So take a really good example. This image I got it from internet. The first image is the modeling that people are really good in. Mostly engineering bachelors are really good in making any geometry with the dimension. CATIA, ProE, SolidWorks, AutoCAD, we always make it. But when we're talking about the mesh creation, why we are doing this, people don't know. So that thing we will discuss, and then you will define the boundary partition, everything to give to the computer to get the outcome of the result. So till now we are confused with the mesh creation, why it is really necessary. So let's talk it is. So here, if you imagine there is a pipe flow, this is a normal continuous domain. You will try to make it into small segment, and that we call it as a control volume. This control volume, we will say here we will give all the equations, all the governing equation, and that will pass the information to nearby, and then it will reach up to end of the domain. Then it will give you final outcome. So just take example why grid is really important. You can see one picture, really good picture. This is 8 by 8 matrix, and here we are talking about the 64 by 64. Why they have increased the numbering of the volume, control volume, and it is lesser. You can see the pictures here. This is a one equation, one way I will tell you what is first order of wind and second order. These are the approaches in the solving part. Just look at the images. There is two type of messing. You can see there is a disturbance in the results. Okay, one thing you must be clear. Whenever you are using any CFD tool, definitely it will give you a result. It's not always true you are getting a correct result. For that, you must understand whether you have coded all the data properly or not. It's all about the prompt you always give to the any Google search engine. Whatever prompt you give,
एडमिट कर
it
रहे
will give you
मल्टीपल पेपर
automatically the
कराइए
result.
इधर
Here also you have to give a proper messing prompt. Then only you can get the proper result. So you can see the difference just by increasing the grid. You can see different kind of results. So which one is correct? How would you analyze it? By the discretization methods and the validation part. So discretization method is a
बैकग्राउंड ला
process
लाइन
of
आज करो
converting
लेते
governing equation into
कॉलेज
discrete
मध्ये
means
वाटते
small segment. So you are what you are doing, you are doing the continuous flow domain into smaller manageable segment to get the approximate solution, not the exact solution. So what is the need of discretization? It deals with the PD to convert to discretized form. That computer will solve, and then this transform this PD, and you can alter multiple stability technique also. We'll discuss. So now you can see you are here. You're thinking about some equations, some problem that all about analytical equation. You made in a discretization form, and then the problem will be solved by the computer. So discretization can be three types: either finite different method, or finite element method, or the volume method. How would we decide these things? Based on your problem statement, whether you are talking about the composite material, whether you are talking about the combustion, whether you are talking about the high speed or thermal related issue. You have to decide the problem, then you will choose the discretization technique. This discretization technique will pass the information to nearby whatever the elements are there. So how would you decide? Based on the problem statement. So I am giving you a very good example. Just imagine this is one single room. Don't think these are the multiple one, two, three cells we are talking about. It's a single room, and imagine you wanted to track the temperature here at the blue point. So if you are giving the input condition on this front cell, front wall, and the output condition in this way, you cannot anyway track in the middle temperature. What you will do, you will discretize into multiple segments so that you can get the nodes, corners available. And once you will say to the computer, okay, give me this node at this point, it will give you the intermediate
मला
result.
ऍडमिटच कधी
That
नको
is
घ्या
not at all possible in the real world experiment. You cannot predict what is going on, how the combustion has flowed, how the blast has happened. Now recently the Ahmedabad blast has happened, no one can understand. They will simulate the same situation, they will trigger it, and then they will try to get the information what was the cause of the problem. So this is all about the discretization. How would you discretize? That will bridge the gap between continuous world to the discretized word. We will make in a singular form, small segment. So here there are three modes we can do. This is FDM, finite difference method, finite volume method, and finite element method. In all the cases, you will use to approximate the solution. So how would you do it? In all the cases, there would be a control volume. You will define it, and then you will analyze it. So if I am talking about the finite difference, people always choose the finite difference when they are more focused on the approximate solution related to the difference approximation or the structure way. Like any structure, simpler structure, you can go with the finite difference. Multiple softwares available, complex geometry you can solve anywhere, but it will always use the Laplace, one of the Laplace
अच्छा
equation, and mostly very
म्यूट के लिए
easy
आज चलने के लिए
solvers we utilize
आज
the
तो चालू करने के लिए
equations,
साढ़े 8
and it always focus on the structured grids. Okay, now if I'm talking about the volume, it is really popular. Here we can solve any kind of thing. All the domain, we small region domain, we can solve very easily, mostly fluid flow heat transfer simulation problems. So FPM is really favorite for me because I have worked on the FPM. And now if we'll compare with the DM, it is somewhat related, finite difference, but it will finite volume is really complex and cost time consuming also, but it will give you really good result. Approximate accuracy will be really good compared to others, and it solves simultaneous equation also. Now the last is finite element technique. Here, all the domain we will define it, but it always handle a complex geometries or where the mesh densities are really important. So it is a really expensive, but here you will get a really good result. And mostly people who are working on the analyzing stresses strain in mechanical structure try to get this finite element. In the ANSYS Fluent also you will see one domain is called mechanical epidel. They made a separate section for the finite element technique. So till now we were talking about, excuse me, we were talking about the discretization, why we will give a small segment to solve the problem, but no one has uh, talked about what type of division we should do. It is not always possible they will give you rectangular form of very small simpler structure. It may be abrupt also. So the distribution of the grid is really important, how we will make it. Now if you can see the bottom picture, the system look like this, and now you made it at the corner. You can see it's not a proper cell form, it is a smaller compared to nearby cell. So how would you say it is having a structured one? So depending upon the technique, depending upon the system problem, we will discretize it, but we will first focus on the grid generation, how it will pass the information. So I'll tell you, if imagine you are standing here and you want to calculate it, definitely if you are going in this way, you will take all the nearby information and then pass to the other. Like this only we used to transfer the data in the simulation and in the like any kind of solver use this
पानी
pattern.
बोतल आँच नीचे
So
पे दबे
structure
शीशे से
can be structural mesh will look really finer. You can see the difference in structure and unstructured one abrupt example I have given. So grid can be structured or unstructured, and many more divisions are available. Before that, you must understand what are the terminology. If I'm talking about the node, it will be at the corners, whatever the division you get. If I'm saying cell center, it will be at the center. If I'm saying cell face, these are the cell face, these are the boundary face, and in total, this is the cell. And this is a simple 2D mesh I'm talking about. Now, talked about the 3D, it would cell will look like this rectangular form. And here you will experience one extra word, that is edge, and the face boundary will be in a 2D. So you can see the nodes are here, this is are the cell, it would be cell center. So you must understand the terminology, because while passing the information, whether you are keeping your equation here at the cell, or whether you are keeping at the edges, the cell vertices, or whether it is passing staggered. So this will change based on the selection of FVM, FDM, and FEM. How you are choosing, that will change everything. So now, if someone will ask what are the point we should consider while doing the meshing, you should focus on the resolution. Don't go unnecessary complex meshing. Whatever is needed, do it. Types of mesh utilize based on your application, and always go with your computer resources. Based on the software license and the computer resources only, you can do it. So if I will give you a certain example for 3D and 2D type meshes, it cannot be always quadrilateral. and hexahedral. It can be tetrahedral, pyramid, triangle, prism, any arbitrary. Polyhedral also can be a mesh type, that grid type, that you have to decide it. Because if imagine I said I am standing here passing the information to this is a straight 2D geometry, you can understand. Now imagine we have one uh, grid here, and nearer to this grid suddenly I got the prism. What will happen? The center of the cell is here, and here the center will change, and information will be compromised. So that will create an error. That is really important. That's why multiple engineer only work on the meshing part. There are separate section for geometry generation, separate section industry always focus on the mesh generation, because that will change the outcome or the result part. So types of grid, if I will say, starting with the structure, unstructured, and certain block structure also, and certain specific aligned flow structures are available. So if I will say the structure grid, it is also having multiple segment. So excuse me, slides are changing. Am I audible? Hello.
Yes, ma'am,
Yes,
you
ma'am,
are
you are
audible.
audible.
Okay, the slides are changing or stuck. I cannot move it now.
Slides
Slides,
not
I'm not
changing.
changing, ma'am.
I think
I think
stuck.
stuck.
uh, I think stuck, yeah. Mhm. Can you stop sharing my screen? Like I cannot do this part. There is a issue. I'm so sorry for this. Yes, I can. I think so. Okay. Can you see the screen now?
Yes,
Yes,
ma'am.
ma'am.
Okay. Sorry for the interruption. I'll share again. So let's go for the types of structure. Starting with the structured grid, it will be two major components. It may be Cartesian, it may be curvilinear. The curvilinear is all about the body fitted. Whatever the structure, body structure having, will focus on that, and then we will refine the structure. It will not be a Cartesian. It may change the shape. Similarly, these are the curvilinear most popular. This wing you always simulate in the system. So that can be divided. It also comes under the structural grid. Even though the shapes are different, near to this you can see we have defined the really finer mesh based on the y plus scatter area, and in the middle it is a bigger one. Why we are doing it? Because we are more focused on the near wall result, not the in the middle result. So you can change the meshing
Hello.
whatever the target area. If imagine I am focusing on that part, why would I invest energy of the cost of the simulation here? So make it accordingly whatever the domain demand. Now go for the unstructured. It can be abrupt, you can say polyhedral, trihed, hybrid, anything. So whatever the domain is needed, whatever the demand, because whenever you see the joints, it is really important to focus on whether the information will be passed properly or not. So that can be triangular, quadrilateral, polygon, hybrid. You can choose any. And this is really important. This block structure that people nowadays doing, they are dividing with the imaginary line in the geometry itself. And what is the imaginary line? What they are doing? If imagine my focused area is the 1, 3, and 5 number. What I will do, I'll not refine the 2 and 4 section. I'll only refine the first 3 and 5 section. That we can do with the broad block structure, again matching, non-matching, and this chimera is all about the composite combination of all. So this is the types of structure you must know. So what we have done here, we made a geometry, we created the small meshing or grid generation to give give the proper information to the grids that can be utilized with the discretization technique, either FVM, finite volume, finite element, and finite difference method. And now you know your boundary condition, whether you are working for the high speed flow, whether you are working for the combustion, whether you are working for the only turbulence or low, extremely low speed flow where the Reynolds number is really less. That are the initial condition you will define to the computer. Now imagine you are ready with these three. What about the computer? How computer can solve the multiple equation, like three governing equation and additional equation whatever you have given? For that you have to give a command to the computer whether you want to utilize which kind of numerical scheme. Like in the second year mathematics, we have already studied multiple Rangigutta method or the Gauss elimination, many more methods available. So now we'll talk about the available solver that will solve all the PDEs, convert into algebraic equation that will be discretized by any method. So here are the multiple small segment you must understand. So if I will talk about two cases only, compressible and non-incompressible. So compressible, I have quoted here four. Imagine Gauss Jordan, CDL, multigrid, and Rui solver. And based on your demand, you will choose it. Now imagine you are choosing the Gauss Jordan. It is a direct numerical method. It's not a iterative. What you can do, you can perform the elementary row operation. You will create a matrix. You will solve and get the linear algebraic equation. Now linear, not you will utilize the linear algebraic equation, and then you will solve it with the row and column augmented matrix method. It's a really easy Gauss Jordan method. Now go for the iterative method. This is a serial method. It will give a iterative solution for the same linear equation and try to reach up to the exact solution. Not possible, we'll try to reduce the error percentage. Now, if you are talking about the multigrid method, why we should choose the multigrid if all the iterative methods are available? Because it is a very good for the convergence. The convergence means you have taken three equations, you are solving together. It should always be in a certain error percentage. It cannot be beyond this error, high frequency error. You have to define this much error only I will accept. Like industry or the researcher always go for the 5% maximum error percentage. That convergence is really important, and it would be rapid because of their solution technique. And now Rui solver is really popular. These two are really popular in compressible flow. This capture the shock and discontinuities also. So it is also a approximate solution. Now talking about the incompressible flow, most of the bachelor focuses on simple algorithm and fewer vorticity stream function formulation. Why? Because in the iterative method, we always couple the velocity and pressure. The simple algorithm couple the pressure and velocity, and then we formulate it and solve it. Because of that, the result will give you, if the point is focused by the, you are talking about the velocity, the pressure variation also will affect the velocity. So that can be satisfied by the simple algorithm only. Very good for the incompressible. You can go for the compressible also, but you have to focus on what are the other criteria. So velocity stream function, it is also one mathematical approach. You will more focus on the vorticities, the small curl velocity you always see in the domain, that is the function. So the selection of the solver will change the result, because it is a simple example I can say. You know the pathway to reach from your company to your home, or your to institute to your home. There are multiple paths you can utilize, but you have to choose the optimum one where you can reach faster, less costlier, and give a proper efficient result. So this is nothing but the selection of the solver who will try to give you the PDE's conversion to the algebraic equation and with less error percentage. So what we have done, we made a physical element. We did certain grid generation of mathematical modeling and then converted into algebraic equation and got the numerical solution. And now what we have seen here, once we compared with the analytical solution, there was an error, and that error we have to justify with the comparison chart. So that comparison chart we'll discuss, we call it as the validation part. So it should not be beyond 5%. So how we can reduce, like how we can reduce this error percentage? There are multiple way I gave you. If you are standing here taking the information from nearby points and passing the information, it can be both mode. Two modes are available, either the explicit mode or the implicit mode. Both will solve the problem. Where in software you'll see the one section was there, whether you want to choose the explicit approach or the implicit approach. If you are choosing the explicit approach, that means if you are standing here taking planning to get the information for point 3, you will take the information from the back end of the 3 to 4 line. These are the information you'll take and give the one information to the unknown of 3. So can I say these are the 3 known data you are utilizing for one unknown data, and you are doing one by one. There is no simultaneous information passing by the system. But if you are talking about the explicit, you plan to calculate the 3. You are taking the information from the backside. Also, simultaneously, you are giving the information to 2 and 4 also. So it's unknown must be obtained by the means of simultaneous solution. In the earlier case, contain only one unknown and three known parameters. So you will choose the approach, whether you wanted to do explicit approach or an implicit approach, how the information will be passed. So this is one more section. And now how would you do the comparison? The result I have taken from my paper. So it is all about, now imagine you have one geometry, you discretize it. Now you made a plot also. Take an example of pressure plot at the wall. What has happened? You can see the black colored dots. These are the experimental data, and the multiple colored data you can see. These are the other kind of models. I told you the models you will choose. So these are the models. So before that you have to more focus on which type of mesh I am doing, whether it is too coarse, moderate or fine. So you can see the values like 1.9 E5, that is 1 million I believe, or 2.5, 3.2. I try to increase the grid number, but once I reach up to this number 3.2, I got that 4.5% error percentage only. That means I can optimize my grid here, I can stop here, no need to go for 1.5 percentage. It's better, because if the industry or the problem can be solved up to 5% and you are getting very good results, do it the initially and then optimize it further. What are the target domain? There are multiple messing categories are available. Based on your domain you can make the messing again further. So do rough meshing like this and go further. So this is one way. Validation is really important in any research or academia. People must understand this part. So now we are done with the understanding of a thermal fluid system. Now we'll talk about how CFD to do advanced analysis. Nowadays, all the thermal fluid system, we always say fluid is flowing, heat transfer, heat dissipation. But the real challenge we know as an engineer is the turbulence that we cannot capture properly, either experimentally or simulation based. So what we will do, we'll try to understand this chaotic three-dimensional wide range length and time scale. There are one DNS software, multiple software techniques are available. These are not needed now, because first you should understand the mathematical representation. So mathematical representation, which technique you should choose, because whenever you'll go and open the software, you will be confused. Okay, there are multiple options for turbulent modeling: Reynolds time average, Reynolds time average conservation equation, maybe Boschke equation, maybe two equation k epsilon or k omega. People go directly with k epsilon k omega without thinking about their basic. So this is all about the turbulence, how to choose the model based on the classification of the problem. So if you are choosing the Reynolds time average, you must say I am only focusing on the mean, that is time average of the fluctuating part, the vortices. If you are choosing the time Reynolds time average with the conservation equation, that means you are more focused on the Reynolds stresses also. So what are what are the points you wanted to trigger in your simulation? You have to choose accordingly. Now Bosenko equation is really popular for the very slow speed or very less Leron number, that is laminar flow, where we will try to trigger about the viscosity, molecular viscosity, or turbulent viscosity. So people should go to this approach, not the Reynolds time average. So selection will not give you proper result. Now the two equation model, the two equation K epsilon is NQ omega is really popular to capture the eddy viscosity model, because what you are doing, you are incorporating the kinetic energy and dissipation energy term extra to the computer, and that we will solve. You already feed three equation: mass, momentum, energy. Further equation you have made it based on your application, like whether it is combustion rate, so species equation you have added. Now you are more focused on the eddy, then you have to add two more equations. So in total you have a five equation that will solve for one particular point, and then will pass on to get the final result. So it is cost, uh, you can say time consuming. So choose your modeling accordingly. So now let's talk first about few tools. So people will say, when should I go for the ANSYS, when should I go for the MATLAB, when should I go for the COMSOL multiphysics? So if you are working on the FEM, go for these platform. Abacus is there, SolidWorks, Simulation, Nestron is there, SimScale is nowadays really popular. You can use these things. Now if you are more focused on the flow analysis, so definitely go for the open form. This is the open source software, you can do it without any licensing, but it is difficult to solve because it have their own library, you have to trigger it. Now ANSYS Fluent, really user friendly. SimScale is also popular in the FEM. Now talking about the FDM, people make their own codes for and take a data from the certain libraries, and then this MATLAB is really popular. Many more softwares available. You can choose whatever you wanted. You can do it. Only what will happen? The display and their UI will change. Their interface will change, but the basic will be the same. You have to focus on pre-processing, solving, and post-processing. So now talking about this CFT advanced analysis, I have taken only one equation, that is turbulent. Now go for the CFD meet industries. How people are more focused on here, like CFD studies, real world application. Now take a one case study. The case study is all about electric vehicle battery cooling. Nowadays, people are more focused on this electric vehicle battery cooling. Why? Because of the overheating as well as safety and efficiency issue. So which approach you will utilize, why you are utilizing, whether you are focusing on the velocity or flow field, or you are focusing on the coolant channel, what are the domain, do it and then analyze it. Now my I worked in this case study, that is combustion propulsion system. People are working on the very high speed, try to reach Mach 4, Mach 3, where you can understand how, what kind of combustion will take place, because combustion is really complex phenomena. If you are giving a fuel and imagine it is not combusting at that particular speed and it will waste your fuel, what is the meaning? You can travel at that speed, but it is not cost effective. That is also one problem. Now nowadays this RD is running in the market, rotating detonation engines, where the detonation software will play the role to give the soft thrust. And what we can do, either we can choose the mixing part, either, or we can understand the combustion efficiency part, or we can understand the emission part. And popularly people are using ammonia or hydrogen as a fuel because of this sustainability part. Now go for the other cases where electronics people, where all the, nowadays I think after COVID you can see people are more uh, dependent on the electronic setups. And what is our role? To cool down the system. So what we can do, we can focus on the cooling, airflow, heat sink. We can focus on where the keep the fans, temperature mapping, how to integrate with the IoT, give a feedback, how we should not use this at higher temperature, there must be a range, like it will shut down the system. These are the one domain people are working. Now really real time fault prediction, it is really trending topic, that is digital twin concept. What we are, what people are doing, they are making the same domain, they are analyzing it not up to end. Just after getting a data, they are optimizing the domain, and they can predict the real time fault prediction. If you are here, you made your computer, and after you are using the same computer for 10 days, 20 days together, at after how many hours it will break, or it will not working, it will release too much heat, you can predict without any real time experiment. So it is really popular digital twin concept. So now talking about the opportunity and researches in education. So let's see trends nowadays. People are not focusing on the messing part. So I would suggest those who have got 20, 30 down the line working on, please go for the physics informed neural network, because this is the one pattern can eliminate the messing part. Now, multiphysics coupling. Coupling part means the fluid structure interaction. Earlier, we were only focusing either fluid or the solids. The coupling is really important. What is going on in between? We used to say, okay, airplane is flowing. What would be the temperature of the body? We never focus on the fluid behavior. Now, in the multiphysics coupling, people are combining both together, and the equation will change. Now people are still looking for the sustainable design with CFT. So if education level, if I will say, try to learn this tool, either any software whatever you like, whether you it's based on the FDM, finite element method, volume method, or the uh, difference method, do it. Do the virtual lab training, online platforms are available. Integrate with the multidisciplinary education, don't only choose your own product. And for the research and academia, I should say there are multidisciplinary fields are available. Smart simulation engineering, AI integrated experts are there. One of my friend was working on the cancer cell growth, so, and the pacemaker or the artificial pump. Many opportunities are available and you can simulate by this software. So if I would suggest the summary and discussion, so what it does, it enables the accurate simulation, optimize the complex thermal fluid system, certain residuals that I said, the errors are available. That convergence also is really important, how it will converge. All the equations should reach up to certain convergence level. Advanced technique, this is an advanced technique. Now imagine, I gave you example, a very good example of messing. One room is there, you will distribute. That room is not running or rotating. Now imagine you have to simulate the fan that is rotating inside the room. Then the messing is also is dynamic. That time you have to focus on dynamic messing support. So certain segments are available, you have to go for the moving boundary, that is dynamic messing support. So messing is different criteria. Once you will do this, then only you can get the same information. Now CFT is evolving based on the simulation database so that we can improve the efficiency, safety and sustainability. And if I will integrate with the 4.0 technology like AI, ML, IoT sensor, cloud HPC, so what we are doing, we are making CFD as a smarter, faster and more predictive. And thus safety is just not a tool, it's a foundational technology driving to the future of advanced thermal fluid system in industry 4.0 era. So in this summary, I would suggest we have started with the multiple segment about introduction, how you should know what are the domains are available, what are the particles, what are the problem statement. Then go for the fundamental, which equation will play the role. Don't ignore the mathematics part. Don't only focus on the one box. What is the any tools is a black box like a calculator. If you will give a wrong command, it will give you wrong result. Now you must understand the physics behind it, what are the equations available, do the proper meshing, give proper solver problems, then you can get the proper result. So these are the summary about all the discussion we have made here. So this is a beauty that CFT can give you. It will give you a visibility to the invisible thing. And by industry 4.0 tool that can reduce the effect of the timing, and the consumption of the computer speed can increase because of the nowadays quantum computing in the picture. People are more learning those also, so that we can speed up the solution part. If it will be, then we will be a win side. So complex mathematics can be solved user friendly also, you can utilize it. So if you have any query, you can email me on this Kumari ambevarma@bopal.ac.in. And thank you so much audience for listening. I'll ready for the Q&A. That's why I close the session early, so that we can discuss properly. Any question?
Dear participants, please ask if you have any query, please ask Dr. Kumari Ambe Verma, or you may type in chat box also.
Yeah, chat box will also work. I'll open it. Any software issue, if someone is looking any equation or anything. uh, Anyone interested to explain about any case study? Because I am ready. Or if you don't have doubt, I can give the case study what I have done so far, a little bit about research for 10
Uh,
minutes.
I think you, ma'am, please continue. I think no participants have any
Okay,
query.
then okay, I'll discuss a little bit about my domain that people will connect why we have discussed a lot here. So let's look at this. One domain we can discuss here, that is the aerospace domain. If whenever you will see the engines available, this is a case study that I said, the combustion and propulsion part. Among that, you can see one domain is the air breathing engines. In air breathing engines, you know, to combust a fuel you need air. So it will not take the onboard air or the oxidizer. You can take air from the outside or the atmosphere and then combust it. So we call it as the air breathing engine. And rest non-air breathing, the very good example is rocket. You cannot take the atmosphere, the oxidizer at out of the space or out of this earth area. So we are my domain is air breathing. Now if you will talk about the engines, can be reciprocating, can be rotating also. So these are the types. Now imagine one category I would like to explain, that is scramjet. This engine is a category of aerospace, and really important part, this will not have any rotating or reciprocating part. No movement at all. There is a simple box is available and you have to combust your fuel. It's not like similar to our IC engine that we have studied. There is a piston cylinder and valves are there, nothing. It is an open channel. You have to do it, and that thrust you have to utilize to run the engine. So if I will categorize based on the aerospace, you can see here this is the earth and we used to run here, that is troposphere, all the aeroplanes runs. And in between the ozone layer just above we'll see the stratosphere where all the high speed flow engines run. So you can see this X-43A was tested by USA earlier first. All were unmanned. Whatever the testing has been commanded till now are unmanned. There was no onboard people. It was tested to check the performance, and all are subscale level. Till now people are working on this domain. So if you will see these comparison, this turbojet and this ramjet and scramjet, so wherever you will see the jet engine, it will have two parts. One is rotor, one is stator. Stator will always be fixed, rotor will rotate. So if you see the turbojet engine, this will rotate the rotor. Multiple blades are available. You might have seen this in many places. And here, this is not rotating. All are stator. So stator, there is no rotating part. This is the ramjet. Now look at this. This is the scramjet where geometry will play the role for all the combustion. So ramjet and scramjet is more common phenomena. But the thing is, you can see that this is M is nothing but the Mach number greater than the velocity speed of air. So you can see Mach number 1. Here Mach number is too extremely high speed. Now the combustion takes place at subsonic level. But here in this scramjet, the combustion also will take place at a very high speed flow. So what will happen to manage this part is really important. So what is the keywords? Weight to thrust ratio will play the role. No oxidizer available, really good. No need to design it. Scramjet always performed with the help of the mixing and combustion efficiency at the same time, because whenever the vehicle is moving very fast you won't have a time to mix it and combust it very quickly. So the issue is residence time is really less, no moving parts, so somewhat good, no need for the replacement. But you have to play with the two things, that is shock jet behavior. How would you make it that can change the performance of the engine? So if someone can see the top image taken from the NASA legacy, here what will happen, if you are running, the air will enter it. Because of the high speed, immediately it will create certain shock boundaries, and this shock boundary will create the pressure difference. And once you will enter to the combustor, you will get the desirable temperature and pressure range, so that you can ignite a fuel immediately without any external support. So imagine you are giving the fuel and take as a hydrogen fuel, you just throw inside the combustor domain and it will combust it. And once it will combust it, it will just give a thrust in the form of movement for the vehicle. So whenever you will see any scramjet, it will start with converging inlet, combustor, and diverging nozzle. And my domain was combustor. So let's discuss more about combustor. So if I said there is no rotating parts, what does that mean? The meaning is the geometry does not have any replacement. You can fix it, only you have to choose a proper grade of material so that the heat dissipation will be really good. Second category is how the fuel injection will take place. So as of now, you might have heard the parallel fuel injection, transverse fuel injection, combined fuel injection as well. So what will happen if I will do the parallel fuel? That means if you imagine this is one box, and this way you consider this is an inlet part and this is a outlet part. What you will do, you will throw the you will just consider this as an inlet. Air is coming very at a very high speed, it will strike with the in between this disturbance, create certain shock waves, and that shock wave you can utilize for the mixing, and these holes we are utilizing for the fuel entry. So what we are doing, we are taking air from here. This is one geometry. Here all the mixing will take place, and then you can combust it,
Ma'am,
and then at the end you can. Yes.
uh, sorry for interruptions, but if you are showing PPT, then it is not visible to us.
Okay, okay. You didn't say. I was saying. I thought it is saying. I mean visible. Oh, I'm so sorry for
You
that.
have not shared your PPT.
Oh, it might be hidden. I guess earlier. Yeah. Now it's visible.
Yes, ma'am.
Okay, okay. Okay, sure. Okay, then I'll continue because it was really important image for earlier cases also. Okay, no. Thank you so much, sir, for letting me know. Okay, so my talk is all about the combustion of scramjet. You can see the subsection starting from the aerospace engine. It can be two type: air breathing, non-air breathing. That air breathing can be reciprocating or jet propulsion. In the jet propulsion, multiple categories are available. So we'll more focus on this scramjet. Now the image is really cool here. You can see what are the spheres available away from the earth. So we live here, that is troposphere, where all the aeroplane fly, whatever the combustor air is needed, you can utilize it. In after the ozone also there is the oxygen available. We can utilize as the oxidizer, somewhat stratosphere here near to the ozone layer. There this scramjet often perform. So you can see two images, I guess. The DRDO, this high speed combustor, they have made a trial also subscale. Here also you can see NASA has tested a long back, but the thing is there is all unmanned vehicle. There were no human involved in both the images or both the engines, or all are subscale. What is the meaning of subscale? A very small scale, not the exact aeroplane size, a very small scale. The people have tested, and recently the DRDO have successfully done at a high speed and lasts for 25 seconds or more than that, I guess 2 minutes. So if I will talk about the engines, if you'll see three engines, any engines, it start with the two things. One is rotating part, one is stationary part. This is the rotating part. You can see most of the people might aware of this jet engine. You can see in the aeroplane whenever you fly, and this is the stationary part. So if it is a rotating and stationary, we call it as a turbogato engines. And now here the ramjet engine, where you will see this part is also fixed and the other part is also fixed. That means two stator. So there is no rotating part. Similarly, you can see this image also for this scramjet, no rotating part. Both are not having any rotating part, fixed in a geometry little bit, and you have to combust a fuel. What is the reason behind combustion? We take a fuel, mix with the air, combust it, and thrust will give to the engine or the whatever the payload, and then it will run. So for that reason, you will be at a high speed. Imagine what will happen. It will air will enter inside the engine. You will mix it, combust it, and then the heat dissipation from it will throw the engine forward. So you can see this M as a Mach number. So if Mach number is greater than 1, that means it is really high speed. What will happen in the ramjet? It will not be at the higher speed, it will be the subsonic level. So it is really acceptable zone where we can mix all the things. The subsonic level, you can mix fuel and air very nicely. But at the end, what will happen? The speed will be really less. Now imagine you are running at a very very high speed, a supersonic speed, maybe Mach 5, Mach 6. And what will happen once you will enter? You can see the Mach number inside the combustor also is greater than 1. That means too extremely high flow is involved. You cannot even think of mixing a thing and combustion. So very residence time is really less. So this is also one challenge. Similarly, there is geometry. You cannot alter a lot because of the material constraint. You have to choose a material that can pass the heat very promptly. So if I will say in total about the engines, so you have to manage the weight ratio, weight thrust ratio, you have to focus on their mixing combustion performance in combination of residence time, also no moving parts. You have to compromise with the geometry constraint, and the only part you can manage is soft jet interaction, that is soft jet interaction. then only we can improve the combustion and efficiency. So this is one really good image you can see taken from the NASA legacy. So any engine here, it divided into three segments. One is the before the combustor and one is after the combustor. Why I am saying before the combustor, you can see the flow is coming inside the engine. A lot of shocks has been created, and that shock will change the abrupt change in the properties of the fuel, this domain, and that will give you a favorable situation like pressure increase, temperature increase, and once you will throw the fuel, it will combust it and give a thrust, and that thrust will be dissipated in the nozzle part and utilized to go forward. So whenever you will see any scramjet engine categorizes into converging inlet, combustor, and diverging nozzles. So now see the image. I'll tell you the image was taken by Wedman et al. The German scientists. They have done experiment in lab. These in the lab scale only, and the length is somewhat 140 or 130 only. So the left side you can see we consider this as an inlet, and this is considered as an outlet. And between there is a fuel injector we have installed. So what we can say, there is a combustor geometry, there is a fuel geometry, and in total we call it as a scramjet combustor. Now the geometry part, you can see the combustor geometry is stationary, no moving. You can see the fuel part, no moving part. But the thing is what we can do, we can alter the behavior of the fuel entrainment. You can be utilize fuel as a parallel entry, you can utilize fuel as a transfer entry, or the both. That can change the behavior also because of their entrainment strategy. So one major important part, whenever the fuel will enter, definitely it will strike with the tip of the combustion, this in between fuel injector. We call it as a strut. That design also plays a role, but designing cannot be compromised with the material part. You have to focus on the material heat dissipation as well. So if we'll do the multiple literature segment, you have to compromise. You have to focus on the large scale vortices also, whether the fuel or the flame are holding or not inside the combustor, whether the angle that you have created are favorable to capture the shock or not. So in all total, you have to focus on multiple categories: the geometrical modification, fuel entrainment strategy. Now imagine this geometrical formation, you made it, and there are multiple research has been done by changing the geometry design, changing the combustor wall angle, disturbance has been additionally created. So now we will more focus on the fuel entrainment, how we can change the fuel entry so that it can be consumed properly, or I can say combust properly without giving more emissions. So if you will see a one image that is the same image, try to understand, made in a 2D form. So here it is a 300 Imagine this is one kind of geometry, made it in a 300 In between there is a strut arrangement. The arrangement has been kept definitely with the top or the left or right corner of the plane. You have to fix it in the middle. At the high speed, it cannot be fluctuate. And here the entry is 50 cross 50 You can see the 50 cross 50 Now I give you all the information. First you have to choose the geometry. Now imagine I have chosen this geometry, and the case is fuel will enter from here. This is the first case. This is the generic case. Now second case, you are planning to incorporate from the wall. This would be the second case. That will be the combined parallel with transfers. So according to the CFD stages, you will start with the pre-processing, solving, post-processing. So in pre-processing, you have done with the geometry part. Now what is the second role? It's a meshing part. Once grid generation, once you are done with the grid generation, what you will do, you will check whether the grid was taken is correct or not. That validation part you will do. Once you are done, you will give the multiple equations solved by the computer and will give you result, and you will analyze it. So I have taken this geometry, and there are two cases. Definitely you have to do the first case, that is done by the experiment. You will do the validation, you will get the result, you will now talk about the innovation part, and then you will compare it. So now if I will tell you in the methodology part, you will make a physical model, mesh configuration or mesh stability you will choose. Now the system has a combustion and the turbulence both. So as we have discussed, First three equation is mass, momentum, energy is fixed. You will add one more that is turbulent, and you will add one more that is combustion. Why combustion? Because here, whenever the fuel will enter, there would be a reaction happening in between that will be needed by the species transport modeling. So species interaction is needed. So combustion modeling you have to choose. So in total till now you got how many equation? Three for the basic. Turbulent will give you two more equation and one equation for the combustion. So in total we got the six equation simultaneously solved by the computer for one single cell, and that will pass on to get the result. So this is the case you will do it, and once you will done with this you will get the result, and the result that I am showing is the lower wall pressure. You can see this wall how the behavior has happened, what are the shock wave generation. So this is the behavior. It will enter at a higher pressure. Once it will strike with the in between disturbance, immediately the pressure drop will be happening, and then due to the combustion and heat dissipation, the variation in the pressure you will see at the lower wall. By this dip and height you can predict the shock wave location also, how it will hit to the boundaries. And what I performed initially, first the missing part, I did the coarse missing, I did moderate and fine. Among them I have identified it is showing 4.5 percentage, and this is the turbulence modeling I have chosen, that is K omega SST. So now imagine you cannot only give one dimension for the comparison, you have to focus on the um, contour plots also, image plots. Now this left image is all non-reactive and this is reactive and taken from the model that Germany researcher has done. Took the same image, and you can see once it hit from this it created multiple shocks, and then the mixing has happened. Now what is the difference in non-reacting and reacting? In this case combustion has taken place, in this case only we are talking about mixing part. So the first one is the DLR experiment, and the rest density and pressure plot I have created in my software. So you can see very good similarity in reacting cases because mixing you can analyze it. Here the reacting part you can see the disturbance in the middle because of the selection of the numerical techniques. Whether you have chosen properly or not, that will change. But if you will see the capture of the software, follow the same trends. So the same thing you have to do with the plot part. What you will do, you will create a multiple lines in the middle. What are the temperature variation at the wall, what are the temperature and velocity variable, how it will behave in this simple pipe flow. You will see there would be a parabolic nature, but what about this case where the high speed flow are involved? So these are the reacting cases. You will see the abrupt reduction in the middle. It's not possible in the normal pipe flow, laminar flow. This is extremely high speed and turbulent flow. That's why you will see the behavior in such a way. And this is the temperature variation. All are having constant temperature, but once where the combustion has taken place, you can see the temperature variation at the peak, and that to 1500 Kelvin. And this is all about non-reacting where the reaction has been not taken place, but the thing is flow is really extremely high, so that also will change the manner. You can see in both the cases. So this is the for the reacting cases, this is for the non. These are all about validation part. You cannot compromise with one line only, just taking the bottom wall and keep it in this way. You have to consider all the dimension, and then you can plot the graph. And in all the cases, whatever I have shown shows the less than 5% error issue. So now, if you are done with the validation part, you are done with the geometry selection part, you give a out demand to the computer and it will simulate based on your solver. So now imagine for in compressor you had taken multigrid or ROE, what will happen? It will give you multiple results, multiple dimensions. So my category was software, Mach number distribution, pressure distribution, species distribution, temperature distribution, and combustion characteristics. So you can see the geometry. The air has entered in the geometry. You can see the blue color. That means there's no variation in the so this what to say Mach number. Now here once it hit the corner, definitely it will create a shock wave. So shock wave have multiple types: shock wave, normal shock wave, oblique shock wave, and mini mode. So once you will see tip, and then immediately one inclination has happened, hit the walls. Hitting the wall means in normal will always be in a 90-degree. It is at an angle, we call it as an oblique soft. So once it will change this property due to the oblique soft wave, you can see the variation. The value of Mach number has changed. Because of the Mach number, pressure will also change. And you can see here, sudden Mach number reduce up to very slow. That means stagnation situation has also been occurred. What is the meaning of stagnation? You know the eddies or the formation of the flow separation where flow will be stagnant and the flow will pass on or ignore that location, and then it will pass all the software further, and in between what you will do, you will enter the fuel at your favorable situation and it will combust it. So this thing is for the beginner level. You can take a geometry, you can make it, and you can simulate it, and you can compare with the multiple wall. Now see this, this is the Mach number at the middle, this is the Mach number at the lower wall. Why middle? You can see the blue color in extremely lesser Mach number. Extremely lesser means due to the favorable situation, it was lesser, nearer to zero. That means you can mix the fuel with the air very nicely and the combustion will take place, and that thrust you can utilize for the further movement. Similarly, you have seen this blue color and the Mach number reduction, you can see because of this recirculation zone. And these streamlines are following the same pattern. Only the recirculation zone was the important parameter that changed the behavior in front of the fuel injector. So if I wanted to look how the fuel has entered, that is hydrogen, inside the domain, it will start mixing with the air and then give a stoichiometric ratio, combust it, and pass the information. So this red color you can see hydrogen has entered at Mach number 1 and then reduced up to 0. That means efficiently mixed with the incoming air and giving proper information, and we call it as a mass fraction distribution throughout the control domain.
Kindly.
Similarly, you will look for the
Special
temperature
guide.
distribution. Once the combustion will take place, sudden peak of the temperature maximum, you can see it
Guide
reaches
fine
at
कुठलं चालतं? ना ना.
2000 Kelvin. It's really
अजून
huge, but it will happen because of the high speed
दोन दोन
combustion.
मीटिंग चालू आहे.
And now let's talk about the mixing and combustion efficiency. Initially, nearer to the fuel injector or
इकडे
spec,
एक्झाम ती
there
चालू आहे
was
बेसिक.
no
इकडे एमपीसी
speed
चालू आहे.
up in
वा
the mixing. Once it start
तर भूक
going
लागली.
away from the injector, it start mixing and sowing at 160 or 150 mm of the combustor length. 100% mixing means all the fuel has been mixed properly, and the combustion efficiency you can calculate got the 92.36 percentage, and the maximum mixing has reached at 155 mm of the combusted starting from the inlet to here. Now, what I said, you have to compare it first with the experimental data that we have done. Now, go further for the new innovation that you can do with a one section wall fuel injector. Now, what you did, you injected a fuel from the lower wall. Mixing will take place at the wall boundary. In the middle, also, you can utilize it further. So, what we will do, we'll again plot it and try to understand the behavior. Now, look at this. In the first case, when there is no involvement of the wall entrainment fuel, you will see only a recirculation zone that is a bigger in picture. But once you entered from the lower wall, it also created a recirculation zone, but the variation in the middle has changed. Very small recirculation zones can be seen. What is the meaning? It is showing really reduction in the space that will impact the mixing efficiency length. So you can see that this image, the shock wave also bypassing this shock wave will create also a favorable situation, and you can see in the plot in the lower wall, abrupt change, the black color shows the parallel, and the abrupt change in the pressure at the lower wall because of the entrainment of the fuel at the wall. That suggests you about the behavior of the pressure as well as the Mach number. Now look at the pressure at the middle, follow the same trend, but because of the parallel and transverse, you can see definitely the pressure will be increased, and upper wall also and lower wall also. And what about the species that the fuel you have sent into the wall here and in the entry side, middle side, how the variation has happened. You can see, okay, lower wall will not be consumed properly because of the restriction at one way, but in the middle you can consume properly. That's why people go for the middle fuel return. But the very important drawback in the parallel fuel injector is the middle strut. That material we cannot utilize twice. Multiple research has been done in the France. They claim it is really difficult to keep in the middle in the suitable material. It is not cost effective. So you can see this temperature variation really at a peak in the middle part and difficult to manage. Now talking about the mixing in comparison to the existing one, you can see mixing has taken place little earlier because of the parallel transfer. But the thing is, performance has dropped. You can see at the end. Mixing has improved, but the performance has dropped. That means the selection of the location was good. So what you can do, you can optimize it the injection location and the behavior how you can change. That can impact the performance because we have already claimed the mixing has increased. Mixing efficiency has increased. What you will do, you will only focus on the combustion efficiency now onwards. So you can change multiple variation, multiple length scale variation you can see, multiple location you can see, angles you can perform. So multiple optimization technique has been done here. So by this you can see the first one I have changed the location a lot from the combustor. Okay, there is a catch here. You cannot give too much difference in both the
What
fuel
of Tanzania?
injector. That will not give you suitable performance characteristics.
This
It
is
may give
meeting
you
चालू है
mixing
काय सांगू सर
properly,
क्या
but
कहा
if
मला
you will look
इकडे पण
for the combustion
अरे भैया
efficiency,
ते स्वीट
it
कॉर्न
will give
मारेगा
you
तो
very
चलो
lesser
चलो
combustion
चलो फिर
efficiency, and where
ये चलो सारा
that will be really less compared to the others. But you have to more focus on with the comparison with the existing model that shows the very high peak 93.46%. So multiple variation has been happened. The mixing location has been changed. Angle you can change, and the properties of the fuel species you can change, and you can understand the behavior by
अंकिता
doing
मैडम ले ले वहाँ
multiple
से अंकिता
optimization
मैडम को
technique.
ले
It was seen that the mixing also nearer to the middle combustor is also playing the major role that can suggest the final outcome. So based on selection of the model of the angle of attack, at the end we have summarized it. So what we have summarized, first we have done the parallel fuel injection strategies simulation where we have done the fuel parallel exactly similar to the experimental one. Then we have changed certain changes in the atmospheric condition. Fuel, we have utilized hydrogen only, and then we
कुछ
have
फ्यूचर होना
identified the 93.66%
इतना है
combustion efficiency with 0.155 mm, the length scale that will need it for the minimum mixing. After that, we have changed the fuel injection strategy. One was going parallel, one was going transfer. In both the cases, you have to be very particular about the pressure entry. When the flow is really at a very high speed, very high peak speed, you must understand how it will enter. You cannot push it. So you have to put on the pressure entry, you have to force it. So we have done the 3 ratio, P transfer versus P parallel as a 3. And after that we identified sudden drop in the combustion. Uh, but our positive point was the mixing efficiency length scale has reduced. So further optimization in the location, slot length degree, the impact of incoming air and everything by changing, it was seen the efficiency we can achieve nearer to 95% and up to 130 mm of the combustion. So I would like to highlight here the combustion efficiency we are talking about only the combustor part, not the full engine, because you have to restrict this part. Full will impacted by the converging hot cell, converging inlet and nozzles also. So here, whatever the data you can see, it's all
कौन
about
कॉल
the
ज्वाइन करते हैं
combustor. So what we have identified from the slides, that the ratio you have to be particular about how you will place the location, what are the locations, dimension is needed. You cannot keep the fuel entry too bigger so that the incoming air will trap the pathway of the fuel entry. You have to particular about the slot, otherwise it will also create a recirculation inside the slot also. What are the angle of attack, where in which angle it will enter and what are the angle of attack of incoming air also. So this is the one case study we have discussed, and the software that has been utilized here is the ANSYS Fluent software for this category. So this is one case study in accordance with this slide that we have discussed here, the case study. This case study 2 you can see combustion and propulsive system categorizes for the example is crank combustor. So you can search any case study accordingly, you can understand it, you can make a new paper, new research idea and many things. So thank you all. I have covered all the segment of the basic fundamental, the student friendly, all the education based governing equation, what are the types you have needed, how to discretize it, and one case study you can understand what are the things you can do. You can choose the CFD flow physics based on that. So thank you for the talk. Yes. Thank you so much.
Dear participants, please ask if you have any question or even any query.
Hmm. I really thank the organizing team for the contact. It was my first FDP, so I created in three major segments. I thank you all. If any question you have, you can email me also. I'm free to respond anyway.
Oh, I think no participants have any question or doubt. So, with your permission, shall I conclude this session?
Yes, yes. Surely, sir. Thank you so much. It
Okay, so
was really
thank you
good
so
talk.
much, Dr. Kumari Ambe Verma ma'am, for such an informative and insightful session on computational fluid dynamics for advanced thermal and fluid systems in the Industry 4.0 era. Your presentation gave us a deep understanding of how CFD tools and simulation approaches are transforming industrial thermal and fluid systems. We truly appreciate the time and effort you took to share your knowledge and experience with us today. So we will now conclude this session. Thank you all for
Yes.
your active participation, and we look forward to seeing you in next session of our MDP on Industry 4.0. Have a great day ahead. Thank you so much.
Thank you so much, sir. Have a great day. Yes.
Dear participants, next session will be started at 3 p.m. and is already feedback link has been already shared on chat. So you may search in chat box and please fill the feedback form and also complete the assignment which will be shared. So